and why they're so prevalent in designs of varying sophistication in FRC environments. Then we're going to be going over some of the relevant jargon and terminology for understanding linkages to familiarize ourselves with what the language of linkages looks like whenever we're communicating with other teams or with judges or with engineers with what we're doing. Next, we're going to be going over the basics of modeling linkages in CAD software. And then we're going to be going over the two most common linkages in FRC, which are the beater bar and the 4-bar. And then we're going to go over two of the more niche linkages that are used in FRC, which are notably scissor linkages and straight line linkages. And then we're going to be going over some insights on how to design linkages to solve problems that don't fit into any of these categories, as well as provide some resources to point you in the right direction if you want to delve deeper into designing custom linkages. Finally, we're going to open things up for a Q&A for the last few minutes of this presentation. Let me just preface the rest of this discussion with a summary about the motivations behind using linkages on robots in an FRC context. Linkages are a way to control the motion of your actuators being your pneumatics, your motors, or your servos, which are usually simple in how they perform, creating a simple, predictable, linear, or rotational movement. Linkages allow you to turn this precise but generic input into a controlled, complex mechanical output. Notably, linkages are also a way to make this motion stronger, faster, or longer than what it would be originally. Linkages are also incredibly useful because they can use pretty much any size and shape of actuation. So you can use any actuator you have on hand, so long as that actuator is defined, and use it to solve pretty much any problem. One of the key elements to FRC is that there are many, many ways to solve a problem. So you're never really forced into using linkages. However, linkages are often simpler, wider, and more robust than other methods for controlling motion. And that's why they see play in varying levels of complexity and in various use cases in any game. An example would be 2008, the first game was Overdrive, where you were meant to drive in circles around the track and place balls on truss structures to secure points. Team 829 here has a robot that's effectively a drivetrain and a bunch of linkages. This is because they found linkages to be more lightweight than any other approach in a game where speed was very important, lightweightness was very important. Here are some of the term definitions that we're going to be using. A rotary joint is any connection between two or more links that allow them to move relative to each other. This is the most common joint, and although there's a sliding joint, which we're not going to be covering here, all of our linkages are going to be made up solely using rotary joints. A fixed link is any connection or distance present in a linkage that is fixed and unchanging relative to the rest of the linkage. Oftentimes, like in the diagram we see here, it isn't a fixed link. It isn't a rigid bar. It's just a relative distance and a relative angle that doesn't change compared to everything else. An input link is any unfixed link that is powered and helps drive the output links. In the examples we're going to be looking at, there is only one input link, although in more complex mechanisms, such as Boston Dynamics' spot walking mech linkage, it's certainly possible for there to be more than one input link in more complex linkages. An output link is or are the links that are driven by the input link or links whose motion we care about. While there are other links necessary in constraining the linkage, which would be the orange linkage in the diagram here, we may not necessarily need them to power a mechanism, and we may not necessarily care about them from a standpoint of looking at the motion of the linkage. In our linkage diagram here, the rotary joints or any of the points or x's that are shown because they offer relative rotational movement. The fixed link is the dark blue link, the input link is the cyan link, and the output link is the green link. And again, we do not really care about the intermediary orange link in these types of linkages. We're only interested in the motion of the green link. Now, just to talk about how to model linkages in your CAD software of choice. Our team uses Autodesk Inventor, and you can see artifacts of that in whatever we have screenshots of our CAD like we have here. In terms of modeling linkages and sketches, for rotary joints, it's as simple as having lines coincident in endpoints of one another. Although modeling the thickness of the linkages is interesting and useful whenever you want to determine and control whenever collisions occur between links or occur between links and the rest of the robot. This will be important for reasons we'll see later. With some trivial exceptions, a full linkage's range of motion cannot be modeled in a sketch. So usually you're only interested in a few snapshots. If you look at the diagram we have here, it's made up entirely out of 2 keyframes in time where the intake is protracted and extended. So because looking at the full range of motion of the linkage is so complex, you just want to care about 2 or more defined points and then just assume that the linkage will behave well in between. Well behaved meaning that it doesn't act crazily during that path in between, which you can verify through the use of assemblies or through reasoning out how the joints relate to one another whenever the linkage is going to be moving. Whenever you're modeling something in an assembly, it is important to consider that the links are acting out in 3 dimensions. So you have to consider how they will interfere. Are you going to be having your linkages be planar within one another? Will they be able to hit each other, or will they be staggered to prevent that interference? You can define all of the rotary joints in a linkage using concentric mates. And if you're using a sliding joint, which we're not going to be using any of the linkages here, but it's something that's more useful in more complex mechanisms, you might have to use a slot mate instead. So now we can open up with the beater bar linkage, which is the simplest linkage, which is why we're opening up our discussion with it. It has a single hinging point, and it rotates and actuates around that hinge. These linkages need to be driven by something, which usually sees a 50-50 split between a pneumatic, a motor, and rarely, and occasionally, because we use it on this year's robot, but rarely, they use other linkages to power the beater bar. The example here is 254 using pneumatics to power their 2016 beater bar linkage. We went for something like this in last year's season, and the aggregation of the error in beater bar linkage caused problems for us later down the road. Before I share stories about how our team has learned lessons about linkages, we're going to be looking at some applications of the beater bar. First of all, beater bar linkages are much easier to use without pneumatics, as it's simple to connect a rotary power source, whereas pneumatics are usually linear power sources, to a link in order to implement a beater bar linkage. As they have less links than other linkages, in some cases only having 1 or 2 links, they're lighter, and they also are faster deployed because the less rotary joints means that there's less friction, and so it can deploy faster than other linkages. The game in which they saw the most play in recent years is probably 2016, where they were used by a lot of high-level teams due to them being lightweight and compact in a game where you had to fit a lot of mechanisms to a very small space. In games like 2016, where defense was also comparatively ineffective at higher levels of play, the fragility of the beater bar linkage, which we'll talk about later, isn't so much of a drawback. In 2022, some teams, especially teams who didn't use pneumatics, like Citrus Circuits, I guess Citrus Circuits didn't use a beater bar, teams like Robo Wranglers, used beater bar linkages to capture balls that were bouncing in the air. This strategy was effective, and the Robo Wranglers team 148 employed it to great success during last year's season. This is team 971, Spartan Robotics' 2016 robot. Here are some design insights for designing beater bar linkages. Beater bar linkages need to be designed to withstand greater forces than other linkages because they are more rigid in nature and therefore less compliant and shock absorbing whenever they encounter a load or some external force. In 2012, another game where there's much less defense than 2022 or 2021, Team 987, the High Rollers, used a beater bar intake to intake the game element, an 8-inch diameter basketball with similar properties to this year's cargo. Even then, anticipating heavy defense, they designed their intake to be incredibly robust, and they made it deploy and retract quickly to minimize the time it was exposed. Another example I can think of that isn't shown here is Team 3647, the Millennium Falcons from here in San Diego, They had a purely aluminum 2021 beater bar intake, and they used it to intake the 6-inch cargo of the Game Changer season to great effect in their skills challenges and some off-season competitions. Now let's move on to the 4-bar linkage, which is the second major linkage which I wanted to discuss. 4-bar linkages consist of a chain of 4 rigid links, all connected by rotary joints. The reason that the 3-bar linkage doesn't exist, interestingly, is that a 3-bar linkage is just an unfixed, unmoving triangle. But once you add a 4th link, the linkage gains a degree of freedom. And so for in general, which we'll talk about later, for every degree of freedom you add to a chain linkage, you need a matching input. And so a 4-bar linkage is interesting and useful because it only requires one input to turn into a complex output. Again, 4-bar linkages are very popular within not just FRC, but general engineering community because they allow you to do so much with simple rotary linear output to turn it into a complex mechanical output. We're going to use this opportunity to talk about 5-bar and 6-bar linkages, which they exist and they're useful. And I've seen some teams use 6-bar linkages. And although they are useful in mechanical engineering, and we'll cover some examples of them being shown outside of FRC, their advantages over a 4-bar are so specific and niche that they don't see much use in FRC. 4-bar linkages are usually driven with pneumatics, although many teams who decided to forego pneumatics this year have found ways to use rotary motion to drive a 4-bar. For example, 1678, which is pictured here, Team Citrus Circuits used a Falcon to power their intake. It's more complex and requires more programming to tune these rotary 4-bar intakes. So now let's go over some of the classifications of the 4-bar linkages. And the 3 classifications that I want to talk about are, first of all, there's the crank rocker, which takes a continuously oscillating, rotating small link, and it converts it into a much larger output link, which oscillates around a much larger arc. The second is the drag link, which has 4 links of approximately the same size, which has a different behavior because it allows all of its links to move freely. A lot of the teams use the drag link constrained to a limited range of motion, although parallel 4-bars are popular in delivery mechanisms because we're talking about the parallel 4-bar now. They are popular in delivery mechanisms because they maintain a constant parallel orientation to the fixed link. And this is useful if you want to keep a game bar oriented level to the ground or some other plane. The main disadvantage of the parallel 4-bar over these other 2 linkages, and these other 2 linkages are much more prevalent because they take up much less space than the parallel 4-bar. And so most intakes you see are drag link or rarely crank rocker. 4-bar linkages, being one of the most popular linkages in FRC, have been adapted over and over again, iterated to meet their fair share of purposes. So just to go over some of the history of the 4-bar linkage, in 2020 and 2021, they found their home in 4-bar over-the-bumper intakes, with which they are more compact than their alternatives, and they're also able to withstand a beating while being made of less heavy materials like polycarb. As a reminder, recall that a lot of the 2016 and 2012's beater bar intakes needed to be made out of aluminum, so making something lighter and more compact is always an advantage in FRC. They have been found in earlier games as well. In 2015, 2018, they were used for grasping onto game elements, using parallel 4-bars to clamp onto the elements of those games. And as far early as the mid-2000s and early 2010s, where there was a lot of ARM-based games in FRC, 4-bar mechanisms were also used to actuate arms, as you can see Team 67 using in their 2005 robot. The first thing I want you folks to understand and to keep in mind when designing a 4-bar linkage. Linkage is to understand how they're going to be manufactured. Again, to make sure that the linkage has mounting holes that are capable of being manufactured to proper tolerances. tolerances that your team is capable of producing. If possible, test in CAD what would happen if your linkage links were manufactured too short or too long. How does your mechanism work if a link is made a 1/20 of an inch shorter, a 1/4 of an inch? Secondly, it is helpful to use additional methods to keep the linkages constrained, to be bound to the maximum and minimum intended extension and retraction for the linkage. Whether this means making your links hit each other, like you can see in the picture of the Cheesy Poofs 254 here, or using outside hard stops, this makes your 4-bar more reliable and more controlled. If you're tight on motors, either because you don't have too many to spare supply-wise, or because you've run out of slots on your PDP or PDH, a good place to convert rotational movement into linear movement is to use pneumatics on your 4-bar linkage. And keep in mind, again, 4-bar linkages are much better suited to use pneumatics than beater bar linkages are. And so you're going to want to use, whenever motors are tight, for whatever reason, you're going to want to use pneumatics to power your 4-bar. Here's some tips for pneumatics in particular. If you have your pneumatics retracted while your 4-bar is at the greatest risk of being damaged, this limits the length of the pneumatic, the effective connection of the pneumatic, and so it won't be bent as much whenever you inevitably encounter defense and have collisions occur. So having your pneumatics be retracted whenever your intake or whatever application is extended or at a greatest risk of encountering danger means that those pneumatics are much less likely to break. Also, having your pneumatics far from parallel when the intake is being deployed and retracted assists the intake in deploying and retracting effectively and reliably. In 254, pictured, has its pneumatic piston perpendicular to the link it is driving. To have your pneumatics barely change their angle in the course of their motion is also helpful because the time for a pneumatic to deploy is proportional to the angle that it has to change. And so if you make it so it hardly changes at all, it'll speed up your process very much. Team 254, the Cheesy Poofs, which is shown here, implemented all of these policies into their 2022 robot. When I personally was designing a 4-bar linkage over the summer, an intake, all I really did was make sure that the intake pneumatic didn't change angle too much. I didn't follow the other policies. This caused a lot of problems for my linkage because it had a much harder time retracting, meaning the pneumatics in the mounting bracket for the intake took quite a beating after being exposed for so long. This problem was so vast and so rooted in the issue of the design that you couldn't fix it with a mechanical solution. But had I gone to the design process much earlier and simply moved the pneumatics and gotten it differently, it would have worked the first time. Scissor linkages use one or more X-shaped linkage chains to amplify a linear motion or to turn a rotational motion into an amplified linear motion. In the example of most hydraulic jacks, scissor linkages only use one stage, which is just one X in this context. But this pattern of X's chained together can be used effectively as seen in this diagram. Some of the notable drawbacks of scissor linkages are the fact that they require extremely tight tolerances. Akin to how a 4-bar linkage requires tighter tolerances than a beater bar linkage, as you add more and more links, this error aggregates. And so by the time you get to the final link, those tolerance errors have built up and may lead to some problems. These problems, notably, are the fact that they are very difficult to keep stable and very difficult to keep controlled, even whenever they are manufactured very close to within 1,000th of an inch of their intended value. They are also very poor at handling high loads where they buckle or stall. This is why it's a very common adage in FRC to avoid the scissor lift, which is whenever you wanted to use a scissor mechanism to lift your robot up. Straight line linkages are probably the rarest linkages mentioned in this list. But I bring them up because they are a lightweight way to replicate linear motion instead of using a slot or any other tool to keep things constrained to linear motion. I've seen teams use this linkage in 2019 in lieu of an elevator, recalling that if you recall that 2019 was a game where you had to deliver one of two game elements at varying heights up a vertical wall. And although these solutions were uncommon, these teams effectively used this design because they were lighter and had a lower center of gravity than an elevator. I can't think of any teams off the top of my head, unfortunately. There are two classifications of straight line linkages. There are imperfect and perfect straight line linkages. Imperfect linkages, like the Roberts linkage shown, require less links, but are only approximations of straight line motion, and they should be considered as such whenever you are designing with them. Either make sure that your designs have very low tolerances required to make sure that these errors don't aggregate, or plan for them and compensate them in some way through the use of other linkages, or to make sure that your design accounts for these errors as a built-in feature and rather than something that you don't consider at all. You can model this, you can trace this path in some CAD software using a direct script, or you can simply care about some of the endpoints like I recommend you do. There are perfect linkages like the Pucelli or Lipkin inverser. These linkages are less common because although they provide perfect motion, they require about twice as many links to do so. And those increased number of links leads to an increased number of friction, like I discussed before. However, they do achieve perfect straight line motion if they're manufactured perfectly. And so they can be considered for teams as well. Generally, the more independent links, such as those in a chain you add, the more degrees of freedom you have. And so designing more complex linkages is mostly involved in the study of degrees of freedom. The more these degrees of freedom you have, these degrees of freedom need to be met with a source of rigidity, which can either be an additional link to reinforce it, or it can be an input link, such as a pneumatic or a motor or a servo. Keep in mind that most bridges involving triangles are all very long linkages that are maintained their rigidity through the addition of extra links. An example of a link with 6 links and 7 joints is the clan linkage, which I show here. The clan linkage takes 2 degrees of freedom, and then it converts it into a locking mechanism. It's the most common locking mechanism, although for some locking mechanisms, such as on Spot and Boston Robotics' Robot Dog, have as many as 4 degrees of freedom, which are all controlled with linear actuators. If you wanted to spend further learning discussing the linkage design and theory that can be built behind 6, 7, and even 8 bar linkages, I recommend you look at these following resources, but I'm going to provide a summary for them here. There is the Chebyshev-Grubler-Kutzbach criterion, which is a way to study the degrees of freedom present in a linkage. This is a general formula that allows you to convert between where the links are and how they are connected, and then turns it into the degrees of freedom that need to be matched with additional lines, additional bars, or with an input, such as a pneumatic or a motor. There is Burmister's theory, which is a method to find the lengths, orientations, and conditions of links in a linkage to meet defined constraints. Since CAD software does a lot of the calculations for you, I didn't emphasize this too much in the presentation because although there are methods to calculate link lengths and link positions to meet certain criteria, all CAD software that's worth its salt does this for you. Finally, if you wanted to take a look into 5-bar and 6-bar linkages specifically, go ahead and check out the respective Wikipedia articles. I noticed that the meeting time looks like it's about to go up, guys. Oh, sorry. Here are some image attributions to where I found all the images that I showed you. And now I'm ready for questions.
Okay, if you guys have any questions, would you like to put them in the live chat and then we can answer them? All right, so our first question is, other than intakes, what are linkages most common used in FRC?
So again, intakes are most linkages can be used for intakes and over the bumper games, but they're also used in claw mechanisms. Sorry. Four-bar linkages are mostly used in claw mechanisms, such as 2018 and 2015. And sorry, 2017, 2018, 20, not just 2017, 2018, 2015 use claw linkages in order to manipulate game elements. And for arm mechanisms like logo motion or rack and roll, which are the games from 2011 and 2009 specifically, those, not 2000, 2007 and 2011, those games used four-bar linkages to control their arms. I've seen teams use 5-bar and 6-bar linkages also in 2014 to control the position of their launcher for the game element of Rebound Rumble. Aerial assist, not Rebound Rumble.
Okay, so it looks like our stream is about to cut off in a second. So if you guys want to put any more of your questions in the chat while we reconnect, and then we'll be able to answer when we come back.
Hey, Vince. Did you run out? Oh, you ran out of time?
Yeah, the time cut. So we just need to. All right, thank you guys so much for sitting through our technical difficulties. Our next question is, do you prototype linkages before developing on your robot? Assuming so, what materials do you use?
I feel like one of the most important things is to make sure that the materials you use in your linkage are consistent with what you plan to use on the final robot. So whether if you plan to have your final robot use linkages out of aluminum, then I recommend you make your linkages out of aluminum because the material properties affect how your robot will work. And so I recommend that you keep the materials that you use to test consistent with the materials that you plan to work with. However, if you're using a beater bar intake, I recommend you use aluminum or some other rigid form of material to make sure that it can physically withstand the beating of competition play. But if you're using a 4-bar linkage or any other compliant linkage for an intake, I recommend that you use polycarb or some other plastic to dampen the blow of other robots' defense.
Okay, thank you. Our next question is, what is your favorite part about robotics?
Honestly, my favorite part about robotics is during build season when you're going through a lot of prototypes and a lot of ideas quickly, and you're going through the decision-making process and the iterative design process to verify whether ideas work, and then perfecting those ideas the best you can in order to make sure that your design is the best it can be.
Okay, and then when developing linkages, do you start with math, calcs, or do you integrate in CAD or Sketch?
Whenever I'm designing a linkage from scratch, I usually start with whatever materials I have or whatever actuators I have to use. Like, for example, if I wanted to make a linkage that needs 4 of the same type of pneumatic, I'd go into the shop and see which linkages which pneumatics I have 4 of. And then I would take the specs of the actuators I have and then implement that into a sketch and then design the linkage from there. Then use the sketch to make an assembly, use the assembly to make some drawings, and then use some drawings to manufacture, prototype, and test the design.
Okay. Thank you so much, Marshall, for your amazing presentation. We also want to thank everyone watching the stream for watching the preseason panels. We have to give a major thank you to all of the teams who have helped us, including Spider, Warlords, and Code Orange for all the help that you guys have given us throughout these panels, and it's been an incredibly educational week, and we hope that you have all gained valuable takeaways from all of the panels that we've done this entire week.